Well, guess what? We're not in school today because it's snowing. But at least it's snowing and there's no ice. So here we go with today's lesson. Because remember what I told you, no more days off. So on BCPS 1 will be a copy of the notes after the slide. I just want to review a couple of things. And then after the slide, there's a note paper. So if you guys could print that out so that you can do the problem with me, or watch it first and then go back and look at that paper and make sure that you print it out so that you have a hard copy of the notes. All right, I just want to go over a couple of things because I'm assuming that on that page 375 out of that old book that there are some questions with getting some of those answers in the right form. Remember, the general solution can be in any form. It doesn't matter. So the general solution, remember, you separate the variables. All right? And so remember, that means you get all of your x's and dx's on one side and all of the y's and the dy's on the other. And the dx and the dy has to be in the numerator. They can't be in the denominator. Then you integrate the left. You integrate the right. Oops. You put plus c somewhere and walk away. So I don't care what you see elsewhere. The general solution, remember, is the family of curves, and it can be in any form. Oops. All right, so it's the family of curves, and it can be in any form at all. All right, now the particular solution is different. The particular solution, I want you in the practice of getting it into y equals f of x. Because on the AP exam, that's the way they're going to want them. So that means after you do this, you have to find C in any form. It doesn't matter. And everybody's C can be different, but ultimately, when you get it into this y equals f of x form, everything will be the same. All right? So you find C, you substitute your C back into wherever you found it from. So into your general form, doesn't matter what it looks like, and then you solve for y, and that's the most important part. All right, so if you have questions, again, email me and I'll try to address them. If I need to scan something in, or I need to put a document up or do another little video, I can do that. All right, on this note paper that you're going to see next, this next slide, you're going to see several examples. I'm only going to do the first two, and then the examples that I give you will review general solution, particular solution, and basically number 1 on here. All right, this is a review from pre-calc, but I'm going to show you how it relates to what we've been doing, and then we'll talk more about this one the next time I see you. So let's look at number 1. It says a particle initially at rest has an acceleration defined as a equals t plus 2. Find the position of the particle at any time t if the position of the particle at t equal 1 equals 6. So acceleration, remember, is the derivative of the velocity, which is t plus 2. So if you see that, look, that is a differential equation right there. So I'm going to separate the variables. I get dv equals t plus 2 times dt, and then I can solve for v, because I can't get from the acceleration to the position directly. I have to go from the acceleration to the velocity, and then I have to go from the velocity to the position. So the velocity is going to be the integral of this, which is just t squared over 2 plus 2t plus c. All right, so the problem is, I know that the velocity is the derivative of the position, so that's fabulous. I can integrate that and get to the position. However, this c is in my way. I cannot integrate this with this c in here. I want to go back and see if I can figure out a spot. Like, is there something in the statement of the problem that will allow me to find c? Sometimes it's blatant. Like right here, it says the position of the particle at t equal 1 is 6, but I don't have that yet. I don't have position, so I can't use that. Sometimes the initial condition is hidden in the statement of the problem. So you can't like blow over stuff. Like you got to read every word. And right here it says a particle initially at rest. So what does that mean? That means at time 0, that v is 0. And there's my initial condition to find the c. So you got to be really careful. So when t is 0, v is 0, so this is not that exciting. C is 0. So I know in this case that c is 0, and here's my velocity function. And now I can use that to find the position, because it's asking me for the position of the particle at any time t, which means I'm looking for a rule. So here we go. I know that the position is dx dt or ds dt, however you want to write it. I don't know why that keeps happening. So I know that I'm going to use x, all right, dx dt. I probably should have used s just for standard position, but I'm not going to use the s because everybody thinks my s's look like 5, so I'm not going to do it. So t squared over 2 plus 2t. I'm going to separate the variables. So I'm going to get this dt over here. And then I'm going to integrate both sides. Blah, blah, blah. So I'm going to get x equals t cubed over 6 plus t squared plus c. Because I'm integrating here, add 1, divide by that power. So that gives me 6. Plus t squared over 2 divided by that gives me just t squared. And then my plus c. So now, before I'm finished, here's my initial condition for that one spot. So I know when t is 1, the position is 6. So I'm going to sub in. Position is 6. T is 1 plus c. So then I can figure out what c is, and then I can plug that back in there. Is that good? So this is 7, 6, we subtract and then sub that in, and then this answer, right, with that c plugged in, is our final position at any time t. And you can go from there, or we can talk about that next time. Remember, I only get 15 minutes for free, so I want to use everything I can do. All right, let's look at the second one. It's going to let me go down. No. All right, so let's look at the second one on here. And I want you to be very careful with this. And I'm hoping I can fit it in here. If not, I'll add a new slide. So in this problem, it says that this isotope decays at a rate proportional to the amount present. So what that means is if Y is the amount of the isotope, this is really terrible, you can't see it at all. Anyway, then dy dt, that's the rate of change, okay, the rate of decay is proportional to, so proportional to is multiplied by a constant, the amount present, which is y. So every time you see something increases or decays at a rate proportional to the amount present, pick a variable to represent the amount. The rate of change is the derivative. It's proportional, so it's k times whatever y is. All right, let me see if I can add a slide in here at this point. Yep. All right, so here we go. I've got dy dt equals k times y. All right, so I have to separate the variables if I'm going to solve for that. So I get dy over y is equal to k dt. I would keep the k over here. So integrate. This is an ln. So this is the ln of y equals kt plus c. Now, normally, I would recommend that you find c before you do anything else. But when the y is in the logarithm, I change that rule. Like, the first thing I would do is rewrite this, even with the c in there, because watch what happens. And it also allows me to take the absolute value off, because when I plug my value in, I'll get the right sign and I don't have to worry about this absolute value. So remember, to get the y out of here, I'm going to rewrite as an exponential. So I get y equals e to all of this. All right, so now we talked about this a little bit yesterday, to those of you that saw, but in this problem, if you have an addition in a power, that came from a multiplication problem. So this came from y equals e to the kt times e to the c. And since I haven't found c yet, this problem right here, this e to the c, is just another constant. So we get y equals c e to the kt. And if you remember from pre-calc, this is the exponential growth decay model. And so from now on, the problem is just like you did in pre-calc. You need to go back and look at the problem. So let's see if I can get the problem back up there. So it says it decays at a rate, the half-life is 24,360 years. Suppose that 10 grams of the isotope were released. So that's the beginning amount of this thing. That's 10 grams were released in the nuclear accident. So that means at time 0, there were 10 grams. So if I go back to this problem, when t is 0, there are 10 grams. So if I sub that in, I get 10 equals c e to the 0. Even though I don't know what k is, the time is 0, so 0 times k is still that. So I get c is equal to 10 because e to the 0 is 1. So my function so far is y equals 10 e to the kt. Now, here's what I would like, because I'm going to stop right there, right? Here's what I would like. I would like you to be able to understand this rate of change is proportional to the amount present, and how this integration here leads you to this y equals c e to the kt, and how I got the c value. From there, we'll review the next time I see you. All right, I just want you to be able to do this much. That is all. And that might also help you with some of the stuff that you did on the homework on page 375. All right, so just that much. Looking back at general solution, particular solution, going back to our velocity stuff, right? And just going backwards from acceleration to position, and then looking at this rate of change is proportional to an amount present, and how that leads to this. That's what I want you to focus on. So I will upload to BCPS1 this video. I'll upload the notes so that you have a hard copy of that. Please print that out. And I'll also upload the assignment. The assignment is not that hard. You should be able to do it okay. All right? See you, everybody. Enjoy your snow day. And juniors and sophomores, let's enjoy our time in the sauna room when we're still in school on June 30th. That's not official, by the way. I'm just saying. Bye.